start. So one thing last time huh, yeah. So one thing I sort of forgot to say last time. I mean, forgot to say, but sort of. So last time, what did we do? Last time we saw these characters of category modules in category O. In fact, I sent an email. I summarized what I did. So today the tutorial PDF file will be updated, or maybe already is updated, and that has on page 1 and 2 a list of topics that I'm covering in each lecture. So I've put that in already. Uh, so last time what we were looking at was characters of objects in category O. We looked at the Grothendieck group, and then I said that. So, and here first of all we said that the characters of the M lambdas are C linearly independent. Then we look at the Grothendieck group, which is over. Of course, it's over. It's a Z module. It's not a C vector space, right? And then we said that well, inside this, we looked at first. Okay, what we proved is that this Grothendieck group, which is formed by it's the free group generated by all the vectors, by all the isoclasses of objects, modulo the addition modulo short exact sequence relations. And we also said that this is isomorphic to, or this is equal to the direct sum of the integer character, like integer isoclasses, lambda and h star, and this is also equivalent to the I get equals actually the Verma isoclasses, lambda and h star. Fine. And then what? So as a consequence, and okay, I'll mention one more thing, but fine. So the corollary that I did not state last time, therefore, is sorry. To state that corollary also, I need everything else. I keep getting some emails. Right? Okay, so now let's go for the new tab. Old enough now. So so to prove this, we did a little more refinement. We said that first of all, you let theta, which is theta lambda, which is just a dot orbit. So let theta be one of these central character classes. This belongs to H star mod. So the set of all central characters is basically in bijection with this, the Harish-Chandra's theorem, and let theta be anything like this. So for theta in this thing, we said that KO. So first of all, we defined KO theta to be the direct sum over W and W, the subgroup of this Grothendieck group, with the isoclasses of W dot lambda, W dot action lambda. Yeah, today most likely you're not in today's long lecture. Okay, so and then what we proved is, so this is the definition. So that this of course means that K, the Grothendieck group, is exactly the direct sum over all theta in H star mod W, K O theta. And what we proved last time, the main thing to prove was that, so we showed, this is one more thing. All right, I should define it here on the bullet point, and we showed that on the level of these smaller subgroups, just over the twisted Ryle orbits, here already you have the KO is the same as the direct sum of the Verma module. Sorry, W dot lambda again. This was the main point, and the way we showed this was using the fact that the decomposition matrix, which is D equals M W dot lambda to L W prime dot lambda. Let's just call it this way. Or I think maybe I gave it a name, lambda 1 to lambda S. I called it lambda I, lambda j. Ij goes from 1 to S. Using the decomposition matrix by showing that So we showed this thing by using the decomposing matrix, by proving that the decomposing matrix is upper triangle. One's on the diagonal, something above the diagonal, for some order, up to these ways. That's what we did. Okay, so that's what we had done. Great. And as a corollary to this is the thing that I did not mention. This is where we start, I guess. Add a corollary. Maybe this should be added to the last lecture. Right? As a corollary, this A, this is a recap is A, and the corollary is part B. And it's just the trivial consequence that because the characters of the Varmas are now related in a very integer invertible fashion to the characters of the simples, since the Varmas were independent, therefore the simples are also linearly independent. In that vector space we call it. Okay. So that was that. Fine. So now today the objective is to say that this decomposition, the category of growth entity group splits into these growth entity groups. That holds. Maybe I should call this star today. The goal of today is to show that star holds on the level of categories, not just on the level of their isomorphism classes or characters or something. We also showed that characters is one-to-one. I'm not writing that down on the level of categories or on the level of representations itself. This is the goal for today, to show that this decomposition of category O's growth entity group comes from the decomposition of category O itself. So I need to define these blocks. What is this O theta is going to be and so on. Okay. So maybe let's start by showing this. Okay, so here is the main, here's the prototype result. Let's see. And let me remind you that that is just for a remember. You don't need to write this but recall that if m lambda, a Varma module, has a simple quotient or any higher state module. Right? Maybe I'll say this. If m lambda subjects onto V, which is non-zero, and V has a simple quotient, which is mu, then we know how the central character acts, or the center acts, on the highest rate element here, and therefore here in V, and on the highest rate element here, which is in the subquotient of V, mj plus 1 mod mj, this is positive. Then chi lambda is equal to chi mu, which is the same as saying that mu is in the dot while orbital lambda. So this fact we remember. Now let me start. Let's now start the this is all part C. Part C. So now let's start with 2. So my goal today in the lecture is to get up till the statement of the theorem, and then in the tutorial we can try and prove it because it's a longish lecture. I want to do as much detail as I can. Okay, so 2. So let me start then with what is the idea behind this? The category O itself holds. So what do you mean by direct sum of subcategories? So yeah, let's see. Maybe okay, let's see. So I can define category. Since we defined O theta, so maybe let me write down the goal. The goal today, a more precise goal is the following. Definition. Fine, maybe I'll start with I'll write down the goal after I make the definition. So given a theta, given the central character or a twisted while orbit, maybe I can even call it theta lambda. Sorry, I should do it on the other side. define the subcategory O theta. So we have been defining this K of O theta, right? The Grothendieck group is the sum of K of O subscript theta. Let me now just make that precise. That's actually going to be K of O theta. So define the subcategory or block theta to be, actually maybe I should just have called it the block, to be the full subcategory. So of O. So first of all, it is objects are objects, and the morphisms are everything. And but the restriction is that of those objects. So we know that every object has a Jordan-Holder series, finite Jordan-Holder series. The composition factors, the simple quotients are LQs. And now what I want to say is the only mu's that should occur come from this crystal order. Those objects of M such that if M has a Jordan-Holder factor M, this means the Jordan-Holder factor. Okay. And remember by the Jordan-Holder theorem that any two maximal chains of submodules will have the same set of simple factors. So if this occurs in one of the chains, it occurs in every chain. If this happens, it implies mu belongs to theta, which is just the value. If this happens, if you have any simple quotient, sub-quotient, then that has to come from the same central character. That is what I mean by these sub-characters. Okay. And the goal, therefore, is to show that the Grothendieck is that the category O itself is a direct sum of subcategories. These subcategories. Where A, this happens, and B, direct sum means. So let me, yes, I want to explain what this means. First of all, I need to define the right hand side, and I need to define the direct sum. So let's define the direct sum. The direct sum simply means that if you have if let's say theta, if I take two different while group orbits, twisted while group orbits, and I take Mj in theta j, in category O theta j. Meaning if I take two modules in category O, such that the first module has all subquotients in this while group orbit, simple factors, and the second module has all simple factors in this one. So the disjoint sets of simple factors, because while group orbits are disjoint. Okay? G axis, and we set this partition disjointly into its orbits. So if this thing happens for j equals 1, 2, then what I want to say is two things. One is there are no maps between them. Obviously, form is either over G modules or category one. And second, there are no extensions between them, which I will explain right now. This is what this means is if you have any short exact sequence, 0 to m. Now the way this is written is sort of strange. It is the extension by m1 of m2. So it means m2 is the sum and m1 is the quotient. And I assume that the short exact sequence is in O. As Teja had shown in the tutorial, they need not be closed under extensions otherwise. But assuming that M is also in category O, any such extension splits. Meaning that that's what we say explicitly. There are no non-trivial extensions, meaning that M is literally isomorphic to M1 direct, M2 direction. So there is some map this way going backwards such that this is identity. It's not just basically it's not just a extension, this is not just a quotient, it is also a submodule which is disjoint from M2. So therefore M is direct. So this is what we mean by this block decomposition, and that is the goal. Okay. So now let's actually start exploring the goal. Let's start with a simple with the most basic case. This is more complicated than what we will need to prove this. But let's start with the simplest, one of the simplest cases. So let's say 3. Should I just say this is? I'll just keep this entire thing as 3. ठीक है, so toy example. ठीक है. Now we study non-trivial extension. Okay, fine. So let's do so toy example 1. So maybe baby case. Okay. So in this case, G is a general semi-simple algebra, but my modules that I want are sort of very nice. They are the prototypical examples. They are highest rate modules. So this, let's call this a proposition. So proposition. Say lambda and mu are in X star with mu not in the same orbit, meaning the orbits are disjoint. Therefore, okay. Let's also fix highest rate modules. Also fix highest rate modules not equal to 0, of course. So this is m lambda goes to v, and m mu goes to u. So they are both non-zero modules. Take a weight. Then, so because these two are different orbits, then am I doing vu or uv? Vu equals x u. So first, we want to do this for every object in different blocks. Clearly, as we just saw by the thing I erased here, if you take any highest rate module and you take any of the subquotients in it, they lie in the same. They have the same central gap. So highest rate modules indeed sit inside. Maybe I should have said that, but I will say that. So all Varma modules and highest rate modules with lambda sit inside the block of W because of what I erased here. So this guy is in O theta 1 or O theta lambda. This guy is in O theta mu, and theta lambda, theta mu are disjoint orbits, crystal orbits. Therefore, I claim that I want to prove that this extension is 0 and hom is 0. Let's at least prove it in this basic. Okay. Let's start. So this is sort of standards of proof. I'll split the proof into various steps rather than 3. So choose fix non-zero. 0 not equals b lambda and 0 not equals fix highest rate vector. Because we will keep writing. So these are of course unique up to scaling. Now, so first of all, we talk about hom. So say 0 not equals phi, and we will get a contradiction in hom vu. Then what do we know? We know that phi of v lambda is a maximal vector in u lambda. Because phi has to preserve weights as well. It's a H module map as well as G module map. So it goes to lambda weight space, and of course n plus acts by 0. So at some point I should start skipping and not mentioning. Okay. So what does this mean? It means that if this thing is maximal vector, then that means that on this vector, on phi of v lambda, the center acts by the center acts by center of UG by lambda. But since this belongs to u mu, and u is a highest rate vector, highest rate module of highest rate mu, this also acts by mu. But how can the center act? By two distinct characters. By Harishchandra, so that's a contradiction. Certainly, non-zero maps cannot exist. Okay, fine. Now the extension part. The extension is sort of it's not difficult, but it requires a little more writing. So let me write this part A. So now let's do 3B. Now say we have a non-trivial, we have an extension. I want to show its flips. So say next, say 0 to u to m to v. So we want extensions of x vu. So therefore v is a submodule, m is the middle, and u is the quotient. Remember that there is the mu is the highest weight here, and lambda is the highest. Sorry, am I doing something wrong? I'm doing something wrong. V is the quotient. Okay, fine. So let's start first. So because these two central characters are not equal, they don't agree on all values, all the elements of the center. So let's just fix Z0 in the center such that the two central characters, the two algebra maps differ. So it turns out that when you talk of using the center to differentiate in these things, you just need that one element Z0. You don't need the whole set. So one element, and what these two scalars, these are both scalars. What these two scalars, they're distinct, that's all that matters. That's all that one needs. Okay, so now fix this Z0. Now, okay. So let's look at, first of all, let's look at the lambda weight space. So u is mu, right? So u mu is a dimension, what about u? You have on mu or lambda? Sorry, what? I want lambda. Which one? U and v are high state modules, of course. So u and v are high state modules. M, of course, need not be a high state module. In fact, the claim is that M is in fact a direct sum of these high state modules. That's the statement. Okay, so let's look at the lambda weight space. First of all, this. Next, now note that m lambda equals u lambda direct sum v lambda. This is one dimension. Sorry, no, that is clearly false. V lambda is a quotient. Let me say the dimension of m lambda is 1 plus dimension of u lambda. Because the dimension of v lambda is 1, and this is a module in category O. So it is H semisimple. Okay. Obviously, again, people should feel free to ask questions if you want to. Okay. Yeah, fine. Let's look at the following. Because I'm going to do something very dear to m lambda. I'm going to apply to this m lambda space the map Z0 minus chi u z. Okay. Moreover, okay, Z0 minus chi mu, not u, Z0. What does this do to m lambda? Let us explore. So m lambda, of course, contains u lambda. What does it do to u lambda? In fact, what does this map do to all of u? Here, somebody should at least answer. This is a non-trivial question. If I get some non-trivial answer. I mean, rather, the question is non-trivial, the answer is trivial. So this element takes not just u lambda, not just the subspace, but the entire high state module to 0. Because u was the chi mu is the central character for u. So of course the center entirely acts by 0. Right? So this element will kill all of a codimension one subspace of u. And the claim is it cannot kill all of m. So first of all, I claim to be pi because that's I forgot. Always the quotient map is going to be called pi, and that's going to be the use. So first of all, kills u lambda because okay. And secondly is non-zero. Since if I map this, so let's look at whatever this is. This m is a G module or UG module. So this is a UG. So whatever this is still sitting inside the UG module. Therefore, it maps to V. Let's look at what it maps. Time. Since this is how much is this? This because it's a G pi, everything here is G module map. So it's just Z naught minus chi mu Z naught pi of m lambda. And because this is a surjection and it's a surjection on every weight space, this surjects onto the one dimension. What is this? This is V lambda. How does the center Z naught act on V lambda? This is just a scalar. Scalar acts by scalar. And the whole point was this scalar is not zero. So this is just rescaling normally. It's one-dimensional space. It's acting by scalar. So of course it's all. So this is not zero because it subjects onto something that is not zero. So it cannot originally be zero either. So it's not zero. Its nullity is whatever this is, codimension 1. So its rank is 1. This is called the rank nullity theorem. We have studied in your algebra. Rank means it's the dimension of the A, right? So therefore, whatever this is, so from this we conclude that Z naught minus chi mu of Z naught applied to M lambda is one-dimensional, is a one-dimensional subspace of what? Well, again, this is a UG module map. This is a lambda weight space. Z naught and chi mu scalars. Everything here is inside the zero weight space of UG. Therefore, whatever happens, it still sits inside M lambda. So M subscript. Right. So that's the first point. Also, I wrote down too much maybe, but the idea is if you take this kind of fix a Z naught first of all. This Z naught is crucial because it gives me a scalar and fix the center of the element Z naught. And now the claim is that this guy acted by Z naught minus chi by this scalar. This guy kills most of this lambda weight space, so the highest weight space here, lambda weight space, and just remains extra weight. Let's give this a name. So say. So now we have finally found M. The goal. What was the goal in all of this? We want to show the extension splits. So we want to produce a highest weight module of highest weight lambda sitting inside here. It means I need a generator of that highest weight module. I need a highest weight vector of highest weight lambda that sits inside. The claim is this. The whole point of this was to find that highest weight vector. Now we will prove that this is a highest weight vector. Things are disjoint. Blah, blah. So it's a direct sum. That's so the whole exercise was first to find that highest weight vector, and now we finished the proof. Then the extension splits. Okay, so now let's see. Let's continue. Now, so the next claim is, so now let's start claiming these things, right? So first of all, this means the next claim is this. What does M lambda map to? Let's see. We just saw it here. So this much. Now we know this is equal to C times M lambda. That's what we just said. M lambda therefore maps to V lambda. What does this mean? It means M lambda cannot be in the kernel of phi. So this is a vector that's sitting outside of the kernel, which means I can certainly write down, it's certainly not in the U, so it's not in U lambda either. Therefore, M lambda, the whole thing, first of all, is U lambda, direct sum CM. First of all, it is indeed not inside the kernel, this is indeed outside, and you have a vector space decomposition, the weight space. First. Secondly, claim M lambda is maximum. Is a is a maximal weight vector, maximal in M. Of course, it subjects on to something that's maximal vector in the highest weight module 3, but it itself is now maximal in M. So we are going towards the fact that this is going to generate a highest weight module, which is the complement of U. So we are getting. So first we have to start proving on that. First we just showed that it doesn't lie in U. Now we show its highest weight vector. Then we will, of course, the highest weight lambda. Then we will look at the module it generates. It intersects. To prove it intersects U trivially, and then we compare characters. So this. So first of all, why is this? So from above, so proof by this part B. What happens by part B? If you look at Z naught minus, do I want to do Z naught? Yeah. Z naught minus chi. Now let's apply this thing to M lambda. Earlier we applied it to the full space. Let me apply it to one element of that space. What do we know? We know that M lambda goes to V lambda. I'm acting by the square of this if you want on M lambda, but fine. M lambda goes to V lambda. So therefore, if M lambda, so what does it go to? It goes to C times V lambda now. Where C is of course this scalar. Not equal to 0. Both key point is C is not 0. Okay, fine. But also, what is this equal to? This is
operators. They can't go into submodule.
Sorry, what?
Racing operators on M lambda is identically 0.
Right. That is the whole point.
So if you start with racing operator, then say if they are going to U,
Yes.
then use this element to direct the quantity use this central element.
That's exactly what I want to now claim is that this is actually equal to chi lambda of Z naught minus chi lambda.
That is fine.
Right. Well, so that's equal to C times lambda. Why is that? Let me say the following. Instead also C times M lambda itself. So we have a non-zero scalar. I multiply C times M lambda. What does this? This also goes to C times B lambda. So far, so. Now I can subtract. So this minus, what do I get? I get Z naught minus the chi mu's cancel and I get this much. I'm just trying this. What I wrote correctly. Again. Now maybe we should do this. I would use raising operators now. Okay, well no, this much is okay. This is all I wrote here. But do I want to claim its maximum or do I just want to directly proceed?
So that whatever submodule M lambda generates, that subjects onto B.
Yeah.
Because
Yes.
G action will commute with this element.
Yeah, sure. That's what I want to do actually. I don't think I want to prove its maximal yet.
And if you put that intersection, you will 0.
That's what I wanted to look at the submodule it generates and prove its direct sum with you. I don't know why I said it's maximal here. Maybe I don't even know. So what I want to show not is this. I want to say here the claim is this. So
But it can be
we will prove that this is a direct sum, therefore of course it's maximal. That will be a consequence. Sorry, okay. So first of all, let me just say that Z naught minus chi lambda of Z naught as n lambda equals 0. So far we have not proved. So by B we know that Z naught minus chi mu goes to this non-zero scalar times B lambda because of all this part. And the scalar here, also if you just multiply the scalar by m lambda, then because m lambda goes to B lambda. So this goes as well. That's all fine. So this goes to 0 in V, which means that this belongs to U. And this is in the kernel of pi, so it belongs to U. But how can it belong to you? This is whatever it is. It's a scalar multiple. Everything is lambda weight space. Sorry. So now what do I want to say? No, wait. But this equals how much? This is. I think I'm just doing some big circular proof.
Look at I is a homomorphism. If this is non-zero, but on the right side that quantity is zero, so that can't happen.
Why not?
We are saying it is going to be.
Yeah.
We know Z naught x by I mean Z naught.
Yes. M lambda is a complement anyway. M lambda is outside.
But by definition, we know Z naught acting on small m lambda is scale at the other scalar times.
Why? That's okay, fine. If you show that, then that's actually maybe that's what I should be doing. Not all. From here, it should directly follow. I should not be doing that. Just think for 1 minute, and then we will do it. So what I'm saying is from here, they're not acting on M lambda, right? So on the whole thing, it gives you this one. In particular, if I look at Z naught, let me just do some calculations here. Minus this thing. Act on M lambda. And I get some scalar times M lambda. Because no matter what you act on, you always land up with a scalar times. So in particular, if I act on M lambda itself, I get a scalar times. Right. So therefore, this implies that Z naught itself acting on M lambda gives me rescales M lambda. The prime times. And all I have to do is solve for that scale. And that's solving is here. Okay, so I think let me just say that. Let me first not say this. Let's give this the equation. Let's give this. I'll just say by B. That was correct. Z naught minus chi mu of Z naught M lambda is contained in Z naught minus times capital M lambda. But that times capital M lambda is C M lambda. So it's contained in C M. Okay. Let's just do that. Okay. What does that mean? It means that so is that this is a scalar times M lambda, so I can take it to the other side. Let's say D times M lambda or something. And now let's map this to whatever. Now map it by pi. What does this map to? It maps to D times V lambda. And this has to be equal to what this maps to, which is chi, which maps to Z naught times V lambda, which is exactly chi lambda of Z. And therefore, the scalar that you get is exactly D equals this scalar. Because this is a one-dimensional weight space, this is a non-zero basis vector, so of course, unique linear combination of the basis vector. So D equals chi lambda, and then now we are done. Okay, good. Now that explains to me why I was stuck here reading the writing stuff. I wasn't comfortable. Anyway, fine. Okay, so what have we done so far? We've said that first the forms are zero. Then we said we start with an extension and fix this Z naught. That Z naught is crucial everywhere. And then we first said that the M lambda weight space, the top weight space here in M is one dimension more than the space here. From this, we identified the M lambda, which we will use to generate the subvolume. First of all, no, M lambda, the center indeed acts by, one can do this for every central character, but I just care about center. Z naught acts in this way. Okay, so now let's right. So now consider. So let's give this module a name. So now let maybe I'll call it V tilde be the module UG times M lambda. This is the submodule G submodule of M itself. Okay. And the claim is that now, of course, U tilde and V. This I claim this is going to be the complement. So let's first prove that this is disjoint from. So if we want to direct sum, so let's so say maybe this is claim T. So let's call this part E. Part E is this. Say what should I say? Let's say M belongs to U intersect V tilde. And look at how do you prove it? See, or look at what happens when Z naught acts on it. So because M lies in U, U is killed by Z naught minus chi mu of Z. That means that M on the one hand from U you get this is chi mu of Z naught times M. On the other hand, because this lies in V tilde, and V tilde is generated by a chi lambda eigenvector, and because multiplying by the center is commuting with anything from UG, Z naught here or your Z naught here, it doesn't matter. Therefore, this will give you chi lambda of Z naught times M. But because these two scalars are distinct, therefore, from this, the fact that they are equal means that M has to be zero. So certainly the modules are disjoint. Disjoint except at zero, obviously. The final thing is to prove that they are it's a direct. But well, maybe I'll keep this. I'll keep the short exact sequence. This was baby example 1. And baby example 2 will be this module M2 comma lambda, which we had discussed over SL2, and then there was this observation made by Raghuram a few classes ago. That is what we discussed. Okay, so fine. So we have this module V tilde, which I claim is going to be the complement. So now let's look at these characters. Right? So on the one hand, so U direct sum V tilde is contained in M because V tilde is a submodule of M, U is a submodule of M, the intersection is 0. So the characters, we know how to take characters. So character U plus character V tilde is less equals character. By the way, when I say less equals for characters, it simply means that this is like a power series plus a power series. This is a power series. Take the difference. In every term by term, the difference is non-negative. In other words, basically, it means that in every dimension, the dimension of the mu weight space here is less equal to the dimension of the mu weight space. That's what character less than character. So if you can show that if you can show the reverse inequality, then you know the character less than, character bigger than. So all the weight space dimensions have to be equal. And we know that one is a submodule of this. If we have a submodule of another with finite dimensional weight spaces, and in every weight space the dimensions are the same, then the submodule is the full one. So all we have to show is the reverse inequality. Okay, so let's see why. So we know that M lambda, which is part of this V tilde, surjects onto M lambda. Moreover, this was part E, part F. This I've just kept the short exact sequence for you to look at, but part F is here. M lambda maps to V lambda. So this is non-zero, this is non-zero. Which means that if you look at UG times M lambda, which is V tilde, obviously maps to you apply lowering operators here, they have to map to lowering operators because pi is a module map. Therefore, this has to map to UG V lambda, which is and so the character of U plus character V tilde is bigger equals the character of U plus character of V. And now, because of the short exact sequence, the characters add up because M is still H semi-simple in category. Therefore, the characters are equal, and therefore, because it's a submodule, equals character. Right? Maybe I'll give this another name, star star, which together with star star implies. What does it imply? It implies that U direct sum V tilde, because that was what it was, containing M, is in fact an equality. This also implies, that V tilde, the character of V tilde, was, first of all, it's bigger than character of V, but from here it's less than the character. Because the character of V tilde is less equals char M minus char U, but char M minus char U is char V. So char V tilde is less equals char V tilde is bigger equals char V because of this fact, equal to char V. And V tilde surjects onto V. So same thing. Like here, U plus V tilde injects into M, but the characters are equal. So they are equal. Here, V tilde surjects onto V, but their characters are equal. So they are equal. And therefore now M is isomorphic to, so M is equal to U plus V tilde, and therefore isomorphic to U plus V. So it took some time, and I got stuck in one place, but yeah, the point is that I don't prove its maximum. I get that for free. I just care about the submodule it generates, as Teja pointed out. And so we have that at least in the baby case 1, because of the baby case 1 is if you have two highest rate modules in different central character blocks or with different central characters, then there are no homs between them and there are no extensions between them. Now let's do baby case 2. This was number 3. I think now I want to do baby case 2. This is all done, blah, blah, blah. So now we do this example that we have discussed earlier, and here we go. So, baby case. Now G is SL2, and I will just look at this example. M equals M2 comma lambda, M2 comma 0, which is UG. So G is SL2, USL2, quotiented by USL2 times E square and USL2. Lambda, which is 0. This is the module. No. We still want to do H minus lambda. So let's do that. H minus lambda. That was the big thing. Everyone must say. So what we already saw, we have seen that this M2 lambda has a composition series, has a filtration, if you will, of chain M to M lambda to Z. This we already saw. And this is basically just, like UG times the E. And this is the image of UG times 1. Down. So this is what it looks like. Okay. So before we do this, a big question. Let's do a calculation in SL2 while. When is it? So solve for lambda, the equation. So there is only one simple reflection. I can call it S alpha. S alpha dot lambda equals lambda plus alpha. How does one get this? What does this mean? It means that lambda plus rho, if you apply S alpha without the dot action, this should be lambda plus alpha. But what is this? So that means that S alpha of lambda equals what? Because lambda plus alpha, what is basically the question, what is S alpha of rho? And S alpha of rho is rho minus alpha. Right? Because rho is 1 and minus 1 is 1. So rho minus alpha, this is lambda plus so rho minus alpha, so rho's cancel out, minus alpha becomes plus here, so lambda plus 2 alpha. And which lambda is this? Here. There's only one lambda for which it reflects, and that's minus alpha. S alpha of minus alpha is plus alpha. S alpha plus alpha is minus alpha. Great. So in this case, what happens is the following. In this case, lambda plus alpha and lambda are related by a dot action. So they have the same central character, and therefore we don't know that they split. In fact, it doesn't split. In this case, so when lambda equals minus alpha, the two modules m lambda plus alpha and n alpha, m lambda, have the same central character. Central characters, they are in the same block basically. Lambda plus alpha equals 0. So they are hence both lie in this block O of theta z. And then it need not split. M lambda, M does not, in fact, not only need not split, it does not split. Maybe I should say, I'll say that here. The SE, the short exact sequence for M, 2 comma lambda. It not split, but in fact, also it does not split. Let's look at the other cases. Every other case. So this is the point that sort of, yeah, I'll say that after this every other case, part, so part C. Otherwise, in all other cases, but for all other lambda, right? These two are different central characters. Chi lambda is not equal to chi lambda plus alpha. So by the previous example we did, this should split. So by maybe case 1, this SES splits. Because all extensions are 0. And what is the splitting? This is what I think Apoorva Khare told us, and this is exactly the observation he had made. In this case, except when lambda plus alpha is 0, you can generate this module by 2 maximal vectors because it's really splitting. It's really a direct sum of 2 high straight modules. So of course it's generated by the maximal vector here and the maximal vector here. So you can generate this one for 2 maximal vectors, provided this condition doesn't hold. And exactly that's avoiding one case where lambda equals 9. Otherwise, splits. M2 comma lambda equals M is congruent isomorphic to M lambda plus alpha, direct sum M lambda, and this is of course highest rate vectors. Let me tell you, lambda plus alpha, the highest rate vector is clear. This is just what? What is the highest rate vector of lambda plus alpha in this module? We wrote it down here. And what is the highest rate vector in this one? That is what one has to write down. This is, somebody correct me if Abraham is here, he can correct me. Somebody can correct me. That's okay, so you can check that this is actually a killed by E. That's EFE plus lambda plus alpha H is what? EF is
minus.
there's a minus. That's a minus. So this should be EF is FE square. So EFE is FEE minus HE, right? Plus lambda plus alpha. Here is not minus.
Plus H is.
EF is FE plus HE. Then here we have forgotten this. Okay, the FE square is 0 because we are quotienting by 0. And H acts on E. So H acts on one, H acts on even answer. Okay. Everything here is acting on one. Oh, perfect. This is not 0. This equal to. Oh, no, yeah, this is E is the maximal. This is the maximal vector because E acting on this. Okay, great. Yeah. Okay, so this is the baby case too. Fine. So now the idea is to do it in this in. Okay, so one can check that no, this should split and it does split and so on, but it splits because of our previous. So now we do this in full generality. So now should I just state the theorem? Maybe I should mention one small thing. So in case one, in the lambda to such so this is the end of this baby example. But maybe I'll write down the remark here. In the case, so if lambda equals minus alpha in M2 comma lambda, then what happens when you act by the central elements? If you act by the center, this is the alpha. If you act by the, so you can check that when you act by the center, by the Casimir element, or by the center, it doesn't kill the full body. Minus chi lambda plus alpha 0, so chi 0 there. M to lambda is not 0 for everything. Okay, for all. Is non-zero for at least something. Second. Oh, good. The theorem is right here. Okay, so at least I'm guaranteed to get to the theorem. In which case, oh, good. Then I can, yeah. Then I can actually, let's do the calculation. So somebody remind me of the Casimir first. I know only one Casimir. I know the entire center of a center is a polynomial algebra Casimir. So let's check what happens at the Casimir. Some are non-scalars. No, the scalar would actually vanish. So yeah, for some. Let's look at the Casimir. What is the Casimir? Somebody. I do want the E part.
It's square plus 2 plus E.
Are you sure? Though by 2 or something?
You can scale it, because in Humphrey's first book, he uses half. In BGG, he scales it.
No, I don't care about the half, but so this is correct. Okay. So this is. I don't want to check this. So check this. Let's call this Z0. Z0 is our preferred element in the center that we use. Belongs to the center of it. How would you check such a thing? It commutes. So this clearly commutes with H, and you should check that it commutes with F and E. Commutes with. Okay, so check this element. So let's check this. So what happens when you apply this to? So when you act by the center, what is chi naught of Z5? The Harishchandra prediction says don't worry about anything with the F in the beginning or E at the end. I just look at this and I act by Z. So, now because there are no scalars, it's just Z. Right? So that means chi naught of Z is 0. So I'm just looking at Z acting on M2 lambda. Let us check. Is my claim true or maybe it's false? Let's see. So Z acting on M2 lambda so here is the point. How does M2 lambda's composition series look like? We have 0 to M lambda plus alpha was 0 to M minus alpha to 0. This is lambda. What happens when you do Z minus chi naught of Z of this module?
4 times.
You see? So anyway, it doesn't matter because chi naught of Z is 0. So it's just a 4 and I don't care about it. The whole point is there is no scalar here. So no matter what coefficient I have, I can just divide by. I just want to check non-zero. Fine. Thank you for checking. So okay, so let's look at this short exact sequence, right? What happens when Z minus, I want to claim that this is non-zero as a module. At least let me look at this part of the module. What happens when Z minus chi naught of Z acts on this? Even without this line of calculation, not this line. Because chi naught is the central character for this guy, Z minus chi naught will kill this. That's the whole point of belonging. This is how the center acts on any Verma. That was lecture 1. Right? Z minus chi naught of Z will kill M naught because that is the central character. How does it act on this module? Not the full module, the quotient module. How does it act on the quotient module?
Yes. Here we can actually make it act on vectors in this module. Because we can D square.
But we are going to act on vectors. That's what the point is here. But okay, how do we act on quotient of the module? In the quotient of the module, again, that has the same central character as this. That was the point of working in this setting. Because it has the same central character, it will also kill this quotient. What does it mean to say it will kill the quotient? It means it will take this module into M naught. So we already know that chi minus Z minus chi naught of Z will take M into M naught. So Z minus chi naught of Z takes M naught. I'll do the other way. It's an upper triangular matrix. It takes M. So it first takes M naught into 0 because it kills it. And it takes M lambda into 0, which means it takes M into M. Okay. The claim is that it doesn't directly take it to 0. That this is not a diagonal matrix, it just takes it to 0. It's a strictly upper triangular matrix like in Jordan's block. So it takes this to something non-zero and then it takes it to 0. So this is like saying that the minimal polynomial of this guy is t squared and not t. If it was just t, it would be diagonalizable. If it's t squared, it's a Jordan block. That's what we are sort of saying. Okay, let's just check. So for this, this is generated by one vector, the vector of 1 bar. If this took 1 bar to 0, it would take everything to 0 because it's generated by one vector and multiplying by center is a module. So just check that it doesn't kill the generator of 1. Z minus chi naught of Z acting on 1 bar is how much? It is 4fe plus h square plus 2h. This is and clearly this is not 0 because e square is 0. So this part will never get 0 no matter what h happens to h. H square plus 2h is 0. Lambda is minus alpha. But minus alpha means minus 2 square plus twice minus 2, which is 0. Lambda was minus alpha, so lambda of h is minus 2. Mention it somewhere. Right, so this is still 0. So this part goes there, but 4, you get 4fe, which is not 0. So indeed, so what all I'm trying to say is, therefore, you have that a power of the center minus the character kills M2 lambda. So Z minus chi naught of z does not kill m2 lambda. It does kill every highest state module in that block. But there are blocks, so but it doesn't kill every module in them. Here is a non-split extension where the z minus this guy kills this, it kills here, but it doesn't kill. You need two powers. This is the idea of it being acting nilpotently on elements of that objects in that block. It doesn't kill every element of the block, but it is nilpotent. So it basically, I'll write this down. But it's square. Sorry, z equals Casimir. If z was a scalar like 1, then 1 minus 1, of course, kills everything. You want the non-trivial central elements, and we have one of those in SL2, the Casimir. Now, let me say in general, the same thing happens in general. So, this was what part? 4C. This phenomena is what happens in general. What happens for all sensible G. There are elements in blocks which are non-split extensions. You don't just always get direct sums of Vermas and you get killed by the character. You have non-split extensions like this. Namely, there exist non-split extensions in O theta. Maybe I can say O theta 0, O theta. For example, O theta 0. There are, of course, certain blocks where there don't exist non-split extensions, where everything is split. But that is for, I don't think I'll get there in this. I don't think I have the time to say that in this set of lectures. So fine. So now, so I've defined. So now let's do this. So now let me define this. Sorry, not. I'll say this motivates. So remember this. I am fixing one central character and looking at extensions between Verma modules or whatever modules of the same central character, of that common central character. If it were different central characters, then we just prove that the extension splits. And then one central character will kill one of them, the other will kill the other. But here they don't split. And that is because they have the same central character. And then you can have powers of that central character needed to kill the module. One power is not enough. So that's what we do. We say now that the definition given that semi-simple G, semi-simple G, and a orbit I will define a different category of modules. In fact, this is the block. This is the actual definition of the block that Bernstein, Gelfand, and Gelfand gave that paper. We did that one because of the similarity to the Grothendieck group form. So this, I'll call it maybe O prime theta equals the set of all objects in O, full subcategory, to be the full subcategory. O with all objects M for which, let's see. Maybe I'll just say this with all objects and I'll write it as a set. Strictly, I should not write a set, but that's easier to write it more precisely. M belongs to O. Such that for all Z in the center, I don't assume M has composition factors coming from theta by crystal value. Right? There exists an integer. Basically, Z minus chi theta is nilpotent. Bigger than 0 such that Z minus chi theta of Z power k acting on M So basically this side. So this is this module M2 comma whatever lambda M2 comma minus alpha would be in the O prime block. It would also be in the O theta block because we explicitly we know what the factors are. But it would also be in the O prime. So this, as I said, was the original definition of BGP. And of course, let me say recall what we defined for O theta. You can paste that. So can you show me O theta? At the before the before the those objects for which is the set of all M O such that M L lambda, let's say L mu greater than 0 implies mu chi mu equals chi theta. Okay. Mu comes from that central character. I mean that. So recall this was a definition. There are some things which are composed only of those Jordan order factors with that central character. And here is the definition that basically says that I can start basically if you think of it this way, I have a I act by z minus chi lambda on the biggest one, I go to the next one. I act on the next one, I go to the next one. So by some point, some power, I'll get to 0. Okay. And I'm saying that a priori for every central element, I can have a different integer. Very broad definition. Of course, the answer is going to be this is going to be the length of n finite. But a priori, we assume this. Now, here is the main theorem. With these definitions, I think I can write down the main theorem. Where should I write it? I'll write it. So this is now, we are now ready. With this Davy example, we could see that the center can act nilpotently, center minus this can act nilpotently on modules. And so that allows us to define what BGG originally defined as the blocks. This was defined in similarity to the thing. I also forgot to say something here. There are abelian subcategories. Fine, I will say that now. So here. Okay. One O theta equals O prime theta. That's the first. So these two definitions are the same for all theta. For all twisted Weyl orbits. And moreover, this is an abelian subcategory. Yeah, this is an abelian subcategory. Second. But these are all abelian subcategories of whatever. The second is the main thing. O, the whole category O is a direct sum of these subcategories. Very good. What does this mean? It means that every for all m in O, m is the direct sum of n thetas. But what? X star 1 with all m theta in O theta. The third is what we started by saying today. Oms and X between different things. So that theta 1 not equal to theta 2, mj belongs to O theta j. Then Om category O m1 m2 equals X category O m1 m2. That is the main theorem for today. Question?
2 is not coming. 2 is direct.
Oh, yes, thank you. Clearly 2 is not coming. O is the direct sum of the O theta. So this is the broad, this is the structure of category. And as a corollary, what we saw was correct is that rotating group of O, of course, is equal to the direct sum of the rotating group of O thetas. And last time what we had said was this is the direct sum of rotating. This is, we defined it in this way. But that was just the same as saying I will stop writing theta belongs to. You see it from the, so the point is what we proved last time, the growth and decline equality is actually the combinator, is the shadow on the level of characters of this actual phenomenon. You just take the character and you get this. The whole module, it's any module in O splits as a direct sum of sum, and then you just take it. That's a isoclastic. There are no non-trivial forms or extensions between modules in different central character blocks of category. And so just to take a step back, we have 10 minutes. I'll continue. I'll try to prove part 1 in the next 10 minutes and then part 3 first and part 2 next. And for that, I will, so in proving part 3, I will play you a YouTube video from an actual Hollywood movie. I'm not even joking. And then, then we will prove part 2. Okay, so, but the point is, this is what I will end up proving today in the next 10 minutes in the tutorial. And after that, next class, tomorrow, obviously, the idea is now, we want to understand category O. In some sense, it suffices to understand the categories. Well, now it suffices to understand these categories. Just like to understand all finite dimensional G modules, it suffices to understand the reducible ones by Weil's theorem of complete reducibility, and then all of those were just the L lambdas for dominant. So the same way to understand category O, you understand objects and morphisms. Well, all the objects are contained are direct sums of objects here. All the morphisms have to be morphisms in here term by term because there are none between. And there are no non-split exact sequences either. So all objects are just direct sums. These tell you that there are no objects other than the products of Cartesian products of ones here, operations separate. These tell you there are no morphisms other than Cartesian products of ones. So that's the whole point of understanding the category objects. So we will now so next time, what I was saying was in the last lecture tomorrow, I will mention, I don't know how much time I will have to prove stuff, but I will mention things about how each of these categories looks like. Each of these categories notice how many simple objects, at most the orbit many simple objects. And the orbit is finite. So there are only finitely many simple objects. Of course, every object is finite length. This is a abelian subcategory. Maybe I should add the words finite length, which is obvious. Please add the words. It's the abelian finite length subcategory. So all objects here are finite Jordan-Holder series. The composition factors have to come from the same twisted Weil orbit. The central character is only one of them, and it acts nilpotently. They not act exactly by zero, but it acts nilpotent on every single object. So all this is all nice, but now how does each category look like? What I will tell you, I don't think I have time to prove it, is each of these guys is isomorphic or equivalent as a category to the category of finite dimensional modules over some finite dimensional algebra. And that is what is the theme of the whole this AIS and of the other many. And so that's where we are going to. And the whole thing is geared towards a conference next year, which is on finite dimensional algebra. So we have to connect it to finite dimensional. Okay, so with all of that done, let me take a 30-second break to erase and prove part 1. So next time the goal is to prove that this is basically modules over a finite dimensional algebra in one. Okay, so let's prove part 2. Yeah. Yes. This is it. 4F. Let's call this 5A. The theorem should start a new number. Okay, proof of 1. O theta is O prime theta. So, okay, I have the reverse notation in my function. I decided to switch it here. Okay, so First of all, let's write any object and with its Jordan orders. So let M in O, maybe M in, okay, let's just have global notation. Say 0 equals M0, contain in M1, and K equals M. So K is what we call the length of M. And Mj plus 1 mod Mj is isomorphic to Mj for host. That's what we, this is the our notation as always. Okay, so now suppose M belongs to O. I want to say that the composition factors come from the twisted diagram. That was called this. That's not an important one, right? Which means what? It means that implies that what this means all mu j are in this theta is some twisted diagram. This W dot. Obviously, mu j belongs to the twisted diagram orbit to generate the orbit, but in one common theta. Great. Now what do we do? Now we just look here. So then Z minus for all, let's say for all central elements. What do you know about Z minus chi theta of Z? This will kill Lj. Therefore, what does it mean? It means it takes Mj plus 1. What is Lmuj? Lmuj is this. It kills this. It means it sends this into the lower object. We are done. Right? So therefore, now we have a, if you look at Mk, which is M, send it to chi Z minus whatever this thing is. Chi theta of Z, Mk minus 1. Now again send it to Z minus the lot to Mk minus 2. And finally get from to M1 to M0. M0 was 0. That's it. So therefore, in fact, not only is this nilpotent, the power that you need is exactly the same power for every element. So Z minus chi theta of Z to the length of M sends M to 0 for all M in O theta for all Z in the center. You don't need to worry about which power will work because category O is finite length. Every object has a given length. And now the same power here will kill every object for every center. What does this mean? It means if you started with the object in category O with all simple factors here, then it is killed by this power. So which means that O theta is contained in the BGG definition. Every object here satisfies the nilpotent. Conversely, and then we stop for 10 minutes or whatever. Conversely, what do we do? So okay, so suppose M is in O theta, so M is in O theta prime. I proceed by contradiction. Okay? O prime theta, sorry, not theta prime. Theta is the same, but not in O theta. That means that if the center minus chi theta, this thing always acts nilpotently for some power. Now I can assume a different power for different set. I don't need it. Okay. But this does not fall in this category. That means that M has some Jordan order factor So using the notation here, there is some j here, I guess. Yeah, and there is this j between whatever such that mu j again. All the notation is from here. Mu j is not, so chi mu j is not chi theta, or mu j does not belong to j. The central characters are different. What do you do if there are two different central characters? Let z naught in z such that then have it. Or choose z naught in z. Take z naught in z such that chi mu j of z naught is not equal to chi theta. No. And let's evaluate. We want to say z minus chi theta of z. So start evaluating. Now, first I will take this guy. This is one thing. And also take, because there is this L uj is there, so it has high state vector. So let's take a high state vector in the X semi-simple module. So let's say M uj belongs to Mj plus 1, whose image generates the whole module. Mj plus 1 not Mj. So take the high state vector in here and just lift it. Let this be the lift. I claim, we are claiming that z minus z naught to some power, because so m is in this case. So there is some power for this z naught minus chi theta z naught. Some power of that gives all of m. I'm going to claim that no power of it gives this one element in it. And therefore, that's a combination. Now, for any k, for any power, k bigger equals 0, let's calculate z naught minus chi theta of z naught. Sorry. And again, I want to do the same thing. I should write this down. Now, write the short exact sequence and calculate. What is the short exact sequence? It is Mj sitting inside Mj plus 1, subjecting onto this, the quotient. And I need to use the symbol pi. So I need to define this short exact sequence and calculate and compute for any k bigger than 0. Bigger equals 0. Okay, so I want to calculate not just z naught minus chi theta of z naught acting on power k. I want no power should kill this element. It is enough to show that no power kills this element after you act on by pi. If this is non-zero, then this has to be non-zero. And that's a contradiction to the definition of O. How much is this? Because of this central elements being module maps, this is just z naught minus chi theta of z naught. Okay. Acting on pi of muj. And what is pi of muj? Pi of muj is the highest rate vector. So let me give that highest rate vector name b muj here. So but now okay, on this is a simple high state module. What does a central element act on this high state module by? Without this, the central element alone, it acts by chi mu j. This scalar acts by this scalar, so there's nothing to change here. But now notice this: these two are non-zero unequal scalars. This is a non-zero scalar. It belongs to C cross. And so, of course, the power of a non-zero scalar does not. So for every single k, this power doesn't kill it, which means I'll just take one line more and 10 seconds more. I.e., this implies z naught minus chi theta z naught power k does not kill. It does not kill a single vector inside the module, so it does not kill the module itself. Mj plus 1. Hence not able. But The whole point of assuming this guy was that there is some power that kills him. That's a contradiction. So that this condition cannot happen. That means that that's the end of part one. Okay, so we will stop here. Sorry. So let me take, actually, we'll take 15 minutes break if we want. We'll start slightly later and end at the same time. So let's start at 12:50 if you want, and end at the same time of 1:40. So I suppose
Can I
you can stop.
Can I stop recording?
Now you can stop.
Okay.